This is lesson 12 of our semester-long series of videos on basic circuit analysis. And today we're looking at inductors and inductor combinations. Inductors are the counterpart of capacitors. An inductor is usually a metal rod with conducting wire wrapped around it. Wrapped around it like this. So current would go into the wire and circle around the rod and come back out the wire. And briefly, what this does is creates a magnetic field around the inductor. So here's this whole thing is the inductor here. So this creates a magnetic field around that rod, and just like the capacitor created an electric field, this creates a magnetic field. In fact, I actually want to review or list the important properties of a capacitor. I'm going to do that over here. Because the inductor is its counterpart, we can directly compare the two then. So if you remember, the capacitor stores energy in an electric field. So right away, we have the inductor is storing energy in a magnetic field. Now you might see inductors, and for example, in phone charging stations. So all the rage now are these wireless charging things, where this would be like on the top of your desk, right? And this is plugged into the wall. And you want to charge your phone, so you come over here and you just lay your phone right on that block. Okay, the way that works is that the charging station, the block, has an inductor in it. And so when you plug it in the wall, that's sending current through the inductor. That creates a magnetic field right in the vicinity of the block. And so your phone is sensitive to that magnetic field. Particularly the phone's battery is sensitive to that magnetic field. And that magnetic field then creates a current and a voltage in the battery, and that charges the battery of the phone. Another example is at traffic intersections, okay, where there are stoplights. So embedded in the roadway are these big inductors, and maybe one of these streets is a side street, and so this is Main Street here, and this is side street. And usually, if it's kind of at night when traffic is not as heavy, Main Street will stay green until the side street senses a car. Okay, well, how does it sense a car? Embedded in side street is a big inductor with that magnetic field, and so when your car drives up over that inductor, that magnetic field senses the large metal object on top of it, and that sense signal is sent to the traffic control, and then side street will get a green light. Sometimes motorcycles do not have enough metal to be sensed. So the resolution there is you'll see riders putting big magnets on their motorcycles, and that will be sensed then in this magnetic field of the inductor. Anyway, coming back to the inductor versus the capacitor, we saw that with the capacitor, Q was equal to C times V. And C was the constant of proportionality there, that's the capacitance. And it was measured in farads. Farads. F. Alright, well, I don't really want to get into the physics of magnetic fields and so forth, so for the inductor, we're not going to have an analogous equation to Q equals C times V. But the inductor is measured in, the inductance is measured, or it's L is the inductance, and it's measured in Henry's. Capital H. I'm more concerned about what's happening externally. Okay, this is the circuit schematic symbol for an inductor. Looks like a resistor, but with curly. This was a capacitor. So externally, for the capacitor, we had one of my favorite equations, I equals C dV dt. So the current through the capacitor, I, is equal to C times the derivative of the voltage across it. Here, we've got the current through it, voltage across it. The voltage and the current switch roles. So here we have V equals L di dt. Not as smooth sounding. But there we go. V equals L di dt. Now, if we have the current and we want the voltage, then we use this equation, L di dt. But if we have the voltage and we want the current, then we can manipulate this equation a little bit. This would be 1 over L times the running integral from some reference point to right now of the voltage plus the original current, the initial condition. For the capacitor, recall, we had V equals 1 over C times the running integral t0 to t, I of tau d tau, plus the initial condition. So sometimes students struggle with this equation. So I just want to comment that we have a running integral of the voltage across it. So we're essentially summing up all of the voltage that has been applied from some reference point in time to the point in time that we're interested in, t, plus the current at that time, that reference time, t0. And again, tau is this dummy variable of integration. Now, from this equation here, okay, we can make two conclusions. And the first is that the inductor is effectively a short circuit at DC. So recall that DC means that the voltages and the currents are not changing. All right, so if the current through the inductor is not changing, then di dt is 0. 0 times anything gives you 0 volts. So what device has 0 volts across it? A short circuit. The capacitor, okay, recall, was an open circuit. At DC. Now the other thing we get from this equation that I've boxed is that the current through an inductor may not change abruptly. That is, it must be continuous. Here, if you recall, for the capacitor, the voltage across a capacitor may not change abruptly. Okay, so the physics of the inductor will do whatever it has to do to prevent the current from changing abruptly. So let me give you a couple waveforms. Again, just like for the capacitor, but this time it's current. So this is current I through a capacitor, through an inductor. Something like this is not allowed. 2 amps, 4 amps, maybe 0 amps. This is not allowed through an inductor. Okay, here you have 2 discontinuous jumps from 2 amps to 4 amps and from 4 amps down to 0 amps. That's abrupt change and the inductor will not allow it. An example of something that is allowed is this. 2 amps, 4 amps, 0 amps. Okay, this is allowed, this is continuous. Now, it's worth noting that there's no restriction on the voltage across an inductor, like there was with the capacitor. So the voltage across an inductor may change abruptly. There's no restriction on it. All right. Now recall for the capacitor, we saw that the energy stored in it was 1/2 CV squared. Now based on what all of the points that we've seen here for the inductor, as they compare with their respective points with the capacitor, maybe you want to guess what the energy stored in an inductor's magnetic field is. So think about that for a second. All right, well, we will work it out here. So we know that power, electrical power, is I times V. And we know now that V in an inductor is this L di dt. So there's V, and we still have that I then. Now the energy is related to the power in that it is a running integral from -infinity to t. dt, d tau, excuse me. And so this is, the L can come out in front. It's a constant, just like C was a constant for the capacitor. So this is now di d tau, I d tau. So the d taus cancel, and we're left with L times the running integral of I di. So when we do that integration, we get 1/2 I squared. So this is 1/2 L I squared. You plug in the t, I squared, and then minus, plug in the minus infinity. Now if we assumed at minus infinity, when this thing was built, or whenever, that it has 0 current through it, right? That's a good assumption to make. Then this term is 0. And so the energy stored in an inductor, is 1/2 L I squared. Is that what you guessed? Right. It should be. You see the L plays the role of C, and the roles of the voltage and the current are swapped. So we've got that guy. All right, let's look at a couple of examples. All right, suppose we have a 12-volt source, a 1 ohm resistor, ohm resistor, and we'll put a capacitor in there as well. That'll be a good review. 1 farad capacitor. It's a big capacitor. 5 ohms, and then a 2 Henry inductor. And we want to know, let's find the energy. Stored in the inductor. And we'll also do the capacitor for a good review. Find the energy stored in the inductor and the capacitor. Alright, well, the first thing you should notice is that this is a DC circuit. And I can tell it's a DC circuit because I have only one source and it's constant. It's a 12-volt source. And there's nothing changing in this circuit. Alright, so that means I can replace the capacitor and the inductor with their DC equivalent models. Okay, so the old part here was that the capacitor becomes an open circuit. So there's the capacitor model. The new part here is that the inductor becomes a short circuit. There's the short circuit model. Now, I'll remind you that the energy in the capacitor was 1/2 CV squared. Okay? And the energy in the inductor, I'll put a C there. The energy in the inductor was 1/2 Li squared. Put an L there for inductor. So, in this new circuit with the blue, the models put in, I'm going to be interested then in what is this current through the inductor, right? That's I, the current through the inductor. And I'm also interested in the voltage across the capacitor. That's V. So I need to find those two things essentially. Alright, so I would recommend you pause the video now and try to figure out how you're going to get V and I. Well, let's identify this node here. Call that node 1. And observe that no current goes through the 4 ohm resistor. And that's because the capacitor is effectively an open circuit. Okay? So that makes then the 1 ohm and the 5 ohm resistors in series with one another. They exclusively share this node. The current has no option. It goes through the 1 ohm resistor, then it must go through the 5 ohm resistor. So the 1 and the 5 are in series. Okay, and I have 12 volts across that series combination, right, because this is shorted now. So the current I that leaves the power supply, okay, so it travels through the power supply, it travels through the 1 ohm, it travels through the 5 ohm, and that's the current that we want, and it comes back, doesn't go up, comes back through the power supply. So this is one big series circuit now. Right? So our lives are simpler because we've replaced the capacitor and the inductor with their models. So we can say I equals, from Ohm's law, we have 12 volts across that series combination, 1 ohm plus 5 ohms. So that is 2 amps. 2 amps. Now, if I want to get V, okay, I want to get V, well, here's a node, call that node 2, and while we're at it, call this node node 3. And if we like, let's make node 3 ground. So in trying to find V, we're looking for the voltage from 2 to 3. And we're calling node 3 ground, 0 volts. So we're looking for the voltage at 2. Well, we've already said that no current goes through the 4 ohm resistor. So there's no drop across the 4 ohm resistor. So let's find the voltage at 1. Well, the voltage at 1 with respect to node 3 is exactly the voltage across the 5 ohm resistor, because the 5 ohm resistor is connected to nodes 1 and 3. So we have a series circuit and we want the voltage across one of the resistors. We can get that quickly with voltage division. So we'll take 12 volts, and we want the voltage across the 5 ohms, so we'll put that in the numerator, divided by the series combination, 5 ohms and 1 ohm. And that gets us 10 volts. So 10 volts are dropped across the 5 ohm resistor. So again, that's the voltage then from node 1 to node 3. So if we're calling node 3 to be our reference point, 0 volts, right, that makes node 1 10 volts. And there's no drop across the 4 ohm resistor, so that makes node 2 10 volts. And voila, we have V, the voltage at node 2 relative to node 3, 10 volts. Now that finding the energy is trivial, right? So the energy in the capacitor is 1/2 times C, which is 1 farad, times the voltage across it, which is 10 volts squared. Right, so that's 50 joules. And the inductor is 1/2 L, which is 2 Henry, times the current through it squared, so 2 amps squared. So that is 4 joules. And we've got it. All right, well, let's take a look at another example. So suppose we had a 10 amp source, a 6 ohm resistor, 6 Henry inductor, a 2 ohm resistor, and we'll put a capacitor in there for good measure. Four farads. And again, find the energy. Stored in the capacitor and inductor. Okay, again, nothing is changing in this circuit. There are no switches or anything like that, and the sources are just constant. Okay, so we can replace the capacitor and the inductor with their DC equivalents. And if you're asking, well, is something going to change? Eventually we're going to have switches, and are the sources going to change with time? Yes, we're getting to that. But first, we're just looking at DC circuits. Okay, so we've got our resistors there, don't change. Okay, and the new part of this is the inductor becomes a short at DC, and the capacitor is open at DC. Again, if we want the energy stored in these devices, then we're going to want the current through the inductor, and we're going to want the voltage across the capacitor. So pause this video and see if you can correctly find I and V. So here we go. What you should notice is that this is now one big parallel circuit. The 10 amp source is in parallel with the 6 ohm and the 2 ohm resistors. So I here comes this way, and it can't go to the last branch because this is now an open circuit. So I must go through the 2 ohm resistor. So if we want to find I, the current through the inductor, let's just find how much current goes through the 2 ohm resistor, right? So we can get this quickly with current division. So I is 10 amps times the resistor whose current we don't want divided by the sum of the two resistors. So this fraction is 6/8 or 3/4. So this is 30/4 or 15/2 amps. Okay. Again, that's the current through the resistor, but that's also the current through the inductor, which is what we want. Now, we wanted to get the voltage across the capacitor. Well, again, if you want to identify the nodes, that's good. So there are only two. Right? There are our two nodes. And if we call the bottom one ground, our reference, so that's 0 volts, we're after, let me label the nodes, call this guy node 0, call this guy node 1. We want V, which is the voltage at node 1 relative to node 0. So we'll let node 0 be our reference point, 0 volts. And so now we need the voltage at node 1. Well, observe, the resistor the 2 ohm resistor is connected to those two nodes, so let's find the voltage across the 2 ohm resistor. So the voltage across the 2 ohm resistor we can get from Ohm's law. Take the resistance times the current, which we just got, and we get 15 volts. So that's the voltage across the resistor, and again, because the resistor is connected to the same two nodes whose voltage we're looking for, this is the voltage across the capacitor as well. Alright, so now finding the energy is straightforward. The energy in the capacitor is 1/2 times C, which is the 4 farads, times the voltage across it squared, 15 squared. Okay? And the energy stored by the inductor's magnetic field is 1/2 times the inductance, which is 6 Henry, times the current through it squared. So that's 15 halves amps squared. And there you have it. Now let us consider inductor combinations. And so first, review what we found with resistors and capacitors. So resistors we'll put here, and capacitors we'll put here. So we can have a series combination and a parallel combination. Right, so for series combinations of resistors, we saw that the equivalent resistance was R1 plus R2 plus all the way to Rn. That is, the resistors simply add together. For parallel capacitors, we saw that as well. CEQ was C1 plus C2 plus all the way to Cn. Parallel capacitors add. For parallel resistors, we saw that the equivalent resistance was this thing where we take the inverse of the reciprocals. 1 over R1 plus 1 over R2 plus all the way to 1 over Rn, and then again take that inverse. And this is what we saw with series capacitors. One over C1 plus 1 over C2 plus all the way to 1 over Cn, and then inverse. Alright, so now we're going to look at the inductor, how inductors can combine. So first consider this circuit where we have a voltage source and we have inductor 1 in series with inductor 2 and all the way up until the nth inductor. Nth inductor. And then consider a second circuit over here on the right. Okay, we have the same voltage and one inductor we'll call LEQ. So again, the idea of equivalence, this is the third time we're saying this now. If you connect the same voltage source in both cases, you should get the same current. The voltage-current relationship is the same. That's what it means to have an equivalent circuit or an equivalent combination. So on the circuit on the left, this is a big series circuit. So the same current is shared there through all components, so it does not get a subscript. The same current goes through independent of which inductor it's traveling through. It's the same. And here, this is I. Now, for an inductor, well, before that, Kirchoff's voltage law says that on the circuit on the left, V, the source, has to equal V1 plus V2 plus all the way to Vn, where V1 is the voltage across inductor 1, V2 is the voltage across inductor 2, and Vn is the voltage across inductor n. Okay, so that's Kirchoff's voltage law, but we know now that the voltage across an inductor is L di dt. So this is L1 di dt plus L2 di dt plus all the way up to Ln di dt. And I do want to write this more compactly using sigma pi notation. So this would be J equals 1 to n of Vj, and this guy is J equals 1 to n of Lj di dt. Now remember, we said that the I is independent of the inductor. It has no subscript. So di dt can come out of the summation. So we've got V equals di dt times the summation J equals 1 to n of Lj. Alright, and we'll come back to this in a little bit, but the circuit on the right now, nothing fancy here is going on. We just have one inductor, and so the voltage current relationship is V equals L EQ di dt. Now this notion of equivalence means that we can set the V's equal to one another here. So let me do that down here. This equals this V, which is L EQ di dt. Right? And so both sides of this equation have di dt, so that drops out. And we see that the equivalent inductance is just a sum of all of the individual inductors. That is L1 plus L2 plus all the way to Ln. And again, this was for series inductors. Alright, so in this regard, series inductors combine like series resistors. And you can remember that because the inductor symbol looks a lot like a resistor symbol. Now I'm not going to give you any examples here. I assume that you can add inductors. You can combine them just like you've been combining resistors. Now let us look at parallel inductors. So this is the dual to the previous problem. So let's say we have a current source I in parallel, not with resistors, in parallel with n parallel inductors. All right. Well, each one of those inductors is potentially going to get a different current. Call this I1, call this I2, call this IN. And so we've got the power supply current coming up into this node on the top, and then it splits down those branches. All right, but what is the same here for each inductor is the voltage from the top node to the bottom node, right? V. Each inductor has the same voltage because they're in parallel. They're connected to the same two nodes. Right? We'll come back to that now, but consider for now another circuit that looks like this with just one inductor. Again, the notion of equivalence is that if we connect it to the same source, meaning the I's are the same in both cases, then we should get the same voltage there from top to bottom. Alright, so for the circuit on the left, Kirchoff's current law says that I must be a sum from j equals 1 to n of ij, okay, meaning I1 plus I2 plus all of those i's, in. And we said that the currents were this 1 over L times the running integral of the voltage. Plus the initial voltage, the initial current of each inductor. Right, so over here, again, nothing fancy going on. We know that, again, we have 1 over LEQ times that running integral t0 to t of v of tau d tau plus the initial current at that reference point. So, two things here. If we're going to compare apples with apples, we're going to assume that the inductors were initially storing 0 energy. That is, they had an initial current of 0. We could pick any number, but we're going to say they all are the same and they all have 0. So initially, the initial condition here is that they were not storing any energy, so we'll set those to 0. And then the other point I want to make again is that the voltage here is the same across each branch because they're in parallel. So the voltage does not have a subscript, does not depend on the first branch or the second branch and so on. So there are no subscripts in this integral, so the integral can come out of that summation. Like this, times then the summation of 1 over Lj from j equals 1 to n. Alright, so over here we've just got this expression, and again the notion of equivalence allows me to equate the two i's. So let me do that. Like that. And so in either case, I have, on the left side and the right side, I have this integral with v, and the v's are the same. So I can cancel that with that, and I get that 1 over LEQ equals the sum of all of the reciprocals added together. That is to say that the equivalent inductance is the inverse of the reciprocals added together. So you see, this is for parallel. Parallel inductors combine just like parallel resistors. So for both cases, the inductor combines in the same way that the resistor combines. Alright, so I'm going to leave you again with two questions. Question A. Suppose we had a 1 Henry inductor. Then we took that 1 Henry inductor and we put it in series with an inductor of unknown inductance, Lx. What can you say, if anything, about the equivalent inductance here, the series combination, as it compares with over here 1 Henry? Is the series combination here less than, greater than, or equal to 1 Henry, or does it depend on what Lx is? And similarly, suppose we had that inductor of unknown inductance in parallel with our 1 Henry inductor. How does the equivalent inductance here compare to 1 Henry? Is the equivalent inductance here less than, greater than, or equal to 1 Henry? Or does it depend on what Lx is? Think about it. And I'll give you a hint. Since inductors combine the same way resistors do, the answer is the same as if these were all resistors.